Section: Introduction. In this section, we discuss how encouraging large language models, LLMs, to engage in deeper reasoning through a method called chain of thought, COT, and large-scale reinforcement learning, RL, is leading to significant advancements in complex reasoning tasks, such as high-level math problems. We note that models like DeepSeek R10 demonstrate impressive reasoning capabilities by applying large-scale RL to foundational language models like DeepSeek v3 base. Several approaches, including Simple RL and OpenReasoner 0, have also explored RL training on smaller models, particularly the Qwen series, achieving notable improvements in reasoning skills. However, we face challenges in replicating the success of R10 style training on other general-purpose models, such as the Llama series. This raises an important question: what factors lead to different behaviors in base models during RL training? Understanding this could help us connect pre-training with the scalability of RL for reasoning and guide the development of future models that are better suited for reasoning-focused RL. To investigate this, we focus on mathematical reasoning and observe a significant difference in RL dynamics between the Qwen and Llama models. Our initial studies show that Qwen models adapt better to RL scaling, while Llama models often predict answers too early and produce repetitive outputs during training. To explore this further, we conduct large-scale, controlled mid-training interventions on Llama models before RL training. Our results indicate that the quality of the mathematical pre-training data is crucial for effective RL performance. For example, we find that the Mega Math Web Pro dataset provides much greater benefits for RL scaling compared to other datasets like FINEMATH4+. Additionally, using question-and-answer style data and a small amount of instruction following data enhances RL effectiveness. We also notice that adding long COT data during mid-training can create instability in the RL phase. To mitigate this, we refine the RL prompt and implement a gradual increase in response length to stabilize training. To support extensive mid-training, we create a reasoning-focused mathematical dataset with over 70 billion tokens, called Mega Math Web Pro Max, which matches the quality of Mega Math Web Pro. In our experiments with this dataset, scaling up to 100 billion tokens shows that increasing the mid-training budget can significantly improve downstream RL performance, although these improvements may not be immediately visible in standard evaluations of the mid-trained models. We then explore whether we can enhance the Llama model for RL scaling by further increasing its mid-training. We adopt a two-stage mid-training strategy. First, we train Llama models on a high-quality mixture of pre-training data for 200 billion tokens with a constant learning rate. In the second stage, we reduce the learning rate and introduce different data mixtures, short COT, long COT, and a combination of both, to mid-train 3 separate branches, which we later refine through RL training to strengthen their reasoning abilities. We name this model family OctoThinker, inspired by the multi-armed nature of an octopus. Our experiments across various model sizes and 14 mathematical reasoning benchmarks demonstrate the effectiveness of our approach, with both mid-training stages leading to significant performance improvements, especially the first stage, which consistently yields a 10 to 20% increase. Following this, RL training further enhances performance, with each branch exhibiting unique behavior patterns. Notably, our models after RL training achieve performance comparable to Qwen 2.5 of the same size, effectively bridging the gap between Llama and other models that are more compatible with RL. These findings confirm the effectiveness of extensive, reasoning-focused mid-training in transforming Llama into a suitable base model for RL scaling. To promote open research, we plan to release our curated pre-training data, models, and training scripts. As we move into the era of RL scaling, we are prompted to consider what types of foundation models we need. We believe this new phase presents unique challenges for foundation models, and we hope that OctoThinker represents a significant step toward the next generation of AI systems capable of reasoning. In our preliminary work, we identify a key difference in RL dynamics between the Qwen and Llama model families through the lens of mathematical reasoning, providing a solid foundation for our systematic investigation. Section Summary. In this section, we explore the differences in reinforcement learning (RL) dynamics between the Quen and Llama model families, particularly in the context of mathematical reasoning. Our findings indicate that the quality of pre-training data significantly impacts RL performance, and we propose a two-stage mid-training strategy for Llama, named OctoThinker, which enhances its reasoning capabilities and narrows the performance gap with RL-friendly models. Section: Experiment Setup. In this section, we describe our experimental setup for reinforcement learning, RL. We conduct our RL experiments using the Verl framework and the GRPO algorithm. For training prompts, we choose the MATH8K dataset because it offers a balanced level of difficulty and is concise. We set our global training batch size to 128, with 16 rollout responses per query, and a mini batch size of 64 for PPO. The sampling temperature is at 1.0, and we allow a maximum output length of 4096 tokens. Our learning rate is set to 6 × 10⁻⁻⁶, and we set the KL loss coefficient to 0 in the Verl configuration. We find that a sampling to gradient update ratio of 2 results in more stable RL training. We use a simple prompt format of question and answer for our training examples. For our base models, we utilize LLAMA 3.2 to 3B base and Quen 2.5-3B base for R10 styled RL training, as their model sizes are moderate. In our evaluation, we apply few-shot prompting for base language models and zero-shot evaluation for RL-tuned models. We use tasks like GSM-8K, MATH500, Olympiad Bench, and AMC23 to analyze RL dynamics, and we also assess base model performance with additional tasks such as Math, SAT Math, Math QA, MMLU STEM, OCW Course, MAWPS, SVAMP, ASDIV, and TAB MWP. During our RL training with Llama -3.2-3B base and Quen 2.5-3B base, we notice distinct training dynamics. The Quen model shows a steady increase in the length of correct responses, while Llama exhibits unusual behavior, with its average response length dramatically increasing to 4096 tokens. We observe that Llama often starts with boxed and tends to repeat itself until it reaches the maximum length, unlike Quen, which provides coherent reasoning. The evaluation results reveal that the RL-tuned Quen 2.5-3B significantly outperforms its base model across various benchmarks, while LLAMA 3.2 to 3B shows only slight improvements or even declines, particularly on GSM-8K. This discrepancy may stem from differences in their pre-training despite lacking clarity on the details. This leads us to question whether we can adjust Llama's base language models during mid-training to enhance their RL scaling. We aim to explore various mid-training intervention strategies to see how they affect RL dynamics. We plan to investigate the influence of several factors during mid-training on RL performance through direct comparisons. We will look at the quality of math web data, whether QA format data is included, the characteristics of the QA data, the presence of general instruction following data, and the pre-training token budget. These analyses will help us understand the relationship between pre-training and RL dynamics and identify effective mid-training strategies. For our mid-training setup, we will use LLAMA 3.2 to 3B base with various datasets and configurations within a 20 billion token budget. We will apply a cosine learning rate schedule without warm-up, peaking at 3 × 10⁻⁻5 and dropping to 1/10 of that. The default sequence length will be 8192, and our batch size will be 4 million tokens, using the Nanotron framework. We will maintain the same RL setup as previously described unless noted otherwise. The datasets for our experiments are summarized in a table. For the Open R1 dataset, we combine the question and the thought process within specific tags, using line breaks. For general instruction following datasets, we will keep only high-quality conversations, formatted as user and assistant. To support large-scale studies and mid-training, we curate the MegaMath Web Pro Max dataset. This corpus is built using an efficient classifier to select documents from MegaMath Web, refined by a strong instruction following LLM. We randomly sample millions of documents from MegaMath Web, stratified by publication year, and annotate them for their usefulness in mathematics on a scale from 0 to 5. Documents scoring below 3 are labeled as negative, while those scoring 3 or higher are positive. We find that existing classifiers are sensitive to text extraction choices, prompting us to train our own classifier using fast text for efficiency. Our preprocessing pipeline includes lowercasing text, filtering long words, and removing unnecessary characters. We evaluate the quality of our recalled corpus under different thresholds, balancing data quantity and quality, and ultimately select a threshold of 0.4. Given the noisy nature of many documents, we refine the text using LLAMA 3.1 to 70B instruct, resulting in the MegaMath Web Pro Max dataset, which contains about 5.5 times more tokens than MegaMath Web Pro. Our evaluations indicate that MegaMath Web Pro Max maintains comparable data quality, making it a strong candidate for large-scale mid-training. We also considered supplementing our positive seed set with examples from common math problem-solving datasets to enhance the classifier's ability to recall reasoning-intensive content, but this approach yielded only around 20 billion tokens, which we found insufficient in scale. Section Summary. In this section, we describe our experimental setup for reinforcement learning, RL, using the GRPO algorithm and the MATH8K dataset, detailing our configurations for training and evaluation across various models. We also outline our mid-training strategies, including the curation of the MegaMath Web Pro Max dataset, to enhance RL performance by systematically analyzing factors affecting training dynamics. Section on the inclusion and data quality of math web corpora. In this section, we analyze the role of math-specific web corpora in pre-training and mid-training. We find that these corpora, along with their data quality, are essential for improving model performance. Our systematic analysis shows that mid-training on different math web corpora enhances performance compared to the base model, with MegaMath Web Pro and MegaMath Web Pro Max showing better results than FINEMATH4+. After reinforcement learning, RL, training, we observe that mid-training on math web corpora leads to varying improvements in RL performance, with MegaMath Web Pro and MegaMath Web Pro Max providing significant gains, while FINEMATH4+ shows only slight improvements, indicating differences in data quality. We also notice that models trained on FINEMATH4+ exhibit unusual behavior, such as rapidly increasing response lengths and repetitive outputs. Next, we explore the inclusion of question and answer (QA) data. We believe that adding QA data during pre-training and mid-training enhances model performance. We test a mix of web data and QA data in a 9:1 ratio. Our hypothesis is that the reasoning styles from QA data, including short and long chain of thought, COT, improve model performance. We find that while incorporating QA data generally leads to performance gains, these are modest. After RL training, short COT data does not improve performance compared to web data alone, likely due to differences in data distribution, while long COT data shows significant gains but introduces instability in RL training. We also discuss the importance of instruction following data. We believe that including this type of data in earlier training stages is crucial for enhancing the model's ability to follow instructions, which is vital for successful RL training. We combine instruction following data with web and QA data in a 1:89:10 ratio, using high-quality datasets. Our results indicate that including instruction following data helps unlock the potential of short COT data and stabilizes response lengths. However, when added to long COT mid-training, it still fails to prevent declines in RL performance and rapid increases in response length. To address challenges in RL training, we modify the RL prompt template and maximum length scheduler. We introduce a complex template to replace the default simple template, which stabilizes RL training by providing smoother increases in response length. Despite this improvement, we still see performance deterioration in later RL training stages, indicating the need for further exploration. Finally, we adjust the maximum response length for long-caught mid-trained models. We implement a progressive scheduling strategy, starting with a limit of 2,048 tokens and gradually increasing it to 8,192 tokens. This approach significantly stabilizes RL training and improves performance across benchmarks. Section Summary. In this section, we analyze the impact of math-specific web corpora, QA data, and instruction following data on model performance during mid-training and reinforcement learning (RL) training. Our findings indicate that high-quality math web data significantly enhances performance, while incorporating QA and instruction following data improves stability and effectiveness, although challenges remain with response length and RL performance. Section. On the issue of mid-training budget. In this section, we explore whether increasing the mid-training budget can enhance reinforcement learning (RL) performance. To investigate this, we conduct a mid-training run using 100 billion tokens on MegaMath Web Pro Max with a standard cosine learning rate schedule. We evaluate 3 checkpoints trained on 20 billion, 70 billion, and 100 billion tokens. Our findings show that the models trained on 70 billion and 100 billion tokens perform similarly and significantly better than the one trained on 20 billion tokens. After RL training, we consistently observe that increasing the number of mid-training tokens improves RL performance, whether we move from 20 billion to 70 billion or from 70 billion to 100 billion tokens. Next, we consider whether we can transform Llama into a foundation model that is better suited for RL scaling through enhanced mid-training. We implement a 2-stage mid-training strategy. The first stage focuses on steady improvements in mathematical reasoning, while the second stage introduces diverse model behaviors through branching. This multi-stage approach has been shown to be effective in previous research. The flexible setup allows us to start the decay phase at any time, enabling us to select checkpoints without a fixed schedule, which facilitates fair comparisons across different mid-training configurations. Importantly, reducing the learning rate in the second stage enhances the impact of the new data, helping to shape model behaviors more effectively. Since the decay stage is usually shorter, this method also lowers overall training costs. We name this model family OctoThinker, inspired by the octopus's multiple arms, symbolizing its branching capabilities. In the first stage, we focus on building strong reasoning foundations. Our analysis indicates that high-quality tokens are still limited, so we adopt a cautious approach, primarily using high-quality web corpora like MegaMath Web Pro Max and DCLM baselines, along with a small amount of synthetic data. We follow the training settings from MegaMath Llama, reducing the synthetic data proportion and using a constant learning rate for training over 200 billion tokens. We provide specific training configurations in our tables, referring to these mid-training models as OctoThinker base stable. In the second stage, we aim to find the best mix for RL scaling. Building on previous experiments, we identify the quality and quantity of datasets as crucial for effective mid-training and strong base model development. Before entering the decay stage, we conduct controlled mid-training experiments with 10 billion tokens on the OctoThinker-3B base stable model, followed by RL training, to see how different question-answer datasets affect performance. We test 3 QA datasets: MegaMath QA, OpenR1 Math -220K, and OpenNMathInstruct2, in various proportions while keeping a consistent amount of DCLM baselines data and instruction data. Our ablation studies reveal that the source of QA data significantly influences performance. Specifically, OpenR1 Math -220K and OMI2 come from structured datasets, while MegaMath QA is from less curated sources. This highlights the importance of aligning mid-training data with downstream tasks. Therefore, we choose OpenNMathInstruct2 OpenR1 Math -220K, and NUMINAMATH 1.5 as our main QA datasets for the decay stage, as they closely match competition-style benchmarks. We also identify the optimal QA ratio through our studies. We find that increasing the QA data ratio generally improves RL performance, which aligns with our expectations due to the similarity with RL objectives. However, the benefits start to level off beyond a 30% QA mix, with 40% showing diminishing returns due to token redundancy and lack of diversity at higher proportions. Section Summary. In this section, we explore the impact of mid-training token scaling on reinforcement learning (RL) performance, finding that increasing tokens consistently enhances performance. We propose a two-stage mid-training strategy, OctoThinker, which focuses on building strong reasoning foundations in the first stage and diversifying model behaviors in the second, while emphasizing the importance of dataset quality and composition for effective RL outcomes. Section: Final Decay Recipe. In this section, we explore the decay stage of our training process, focusing on two types of learning rate (LR) schedules. The first is a constant LR decay, where the LR stays fixed at 10% of the final LR from the stable stage. The second is a cosine decay, where the LR gradually decreases to 10% of the stable stage final LR. Based on our evaluations during training, we find that the cosine decay method provides more reliable performance, so we choose it as our default for this stage, with specific hyperparameters outlined in a table. During the decay stage, we create three different variants based on the type of data used: OctoThinker Long for long reasoning data, OctoThinker Short for short reasoning data, and OctoThinker Hybrid for a mix of both, all utilizing the decayed learning rate. The data mixtures are also detailed in a table. Next, we assess the performance of each OctoThinker variant against 13 mathematical benchmarks, comparing them to the original Llama base model and the model after the stable stage mid-training. Our results show that each OctoThinker variant improves by 10% to 20% over the original model and consistently outperforms the stable stage model. We note that random and poor performances on difficult benchmarks highlight the importance of post-training. Overall, these findings support our belief that the OctoThinker base series lays a strong groundwork for exploring reinforcement learning (RL) scaling with effective reasoning abilities. We then proceed to train all OctoThinker base models, which include various decay branches and sizes, 1 billion and 3 billion parameters, through a reinforcement learning phase, following our established approach. This results in a set of models specifically optimized for mathematical reasoning. Similar to the decay stage, the final RL-tuned models fall into three categories based on the data mixture used: OctoThinker Short 0, OctoThinker Hybrid 0, and OctoThinker Long 0. The training dynamics of these models are illustrated in a figure. We observe that the OctoThinker Long branch tends to generate longer responses compared to the others, and while it performs slightly worse at the 1 billion scale, it shows better results as the model size increases, particularly at 3 billion. We also investigate how well our OctoThinker models can bridge the performance gap between the LLAMA 3.2 series and the more powerful Qwen 2.5 models in the RL context. To do this, we compare three base models at the 3 billion scale: LLAMA 3.2 to 3B base, OctoThinker Long 3B base, and Qwen 2.5-3B base. Our findings indicate that during the reinforcement learning phase, OctoThinker Long 3B consistently outperforms the original LLAMA 3.2 to 3B model and achieves performance comparable to Qwen 2.5-3B, which is recognized for its strong reasoning skills and extensive pre-training. The hybrid and short branches perform slightly worse, especially on challenging benchmarks. Overall, these results emphasize the significant improvements brought about by our mid-training strategy and confirm that OctoThinker effectively narrows the performance gap, enhancing the competitiveness of LLAMA 3.2 models in mathematical reasoning tasks. In the related work section, we discuss the role of reinforcement learning in advancing language models for reasoning-intensive tasks, such as competitive math. Previous studies have focused on smaller language models, but replicating these successes with major model families like Llama has been challenging. The complexity of pre-training processes complicates our understanding of how they interact with RL scaling, leading to some unconventional research. For example, some studies show that one-shot prompting can improve reasoning in Qwen but has minimal effects on Llama. Our work aims to address this gap by implementing controlled mid-training interventions on Llama models, uncovering key factors that facilitate effective RL scaling. Building on these insights, we introduce OctoThinker through a two-stage mid-training strategy, followed by RL training, resulting in models that match Qwen's performance at the same scale. Finally, we highlight the importance of high-quality pre-training corpora for language models, especially for math reasoning tasks where large-scale mid-training is not feasible without such data. Early open-source efforts have made progress but are limited in scale. The release of MegaMath was a significant advancement, allowing for scalable mid-training in our work. We have curated a new, reasoning-intensive math corpus, MegaMath Web Pro Max, which exceeds 70 billion tokens and matches the quality of MegaMath Web Pro. This corpus supports the first stage of our mid-training for OctoThinker and will be made available to benefit the broader open-source community.